What's going on, YouTube? Welcome back to another Tutortopia video. So in today's video, we'll be going over inhomogeneous ordinary differential equations. So in our last video, we went over higher order homogeneous ordinary differential equations. So we had, for instance, y double prime plus y prime is equal to 0, right? Then we could solve this by saying lambda squared plus lambda is equal to 0. So we get lambda equals 0, or lambda plus 1 is equal to 0, which then goes to lambda equals -1, and then we can just easily get y of x is equal to c1 e to the 0 times x plus c2 e to the -1 times x. So just c1 plus c2 e to the -x. Okay? And then you could solve for c1 and c2 given some boundary conditions, so y of 0 equals 0, y prime of 0 equals 0, something like that, right? So what we're going to go over today is the inhomogeneous part. So basically we're going to be adding some function of the variable that we're differentiating with respect to. So for instance, these y double primes are actually dy squared, is d squared y over dx squared. So I'm differentiating with respect to x, right? And then this one is dy over dx. So again, differentiating with respect to x. And then on this side, we're going to have some function of x as something called a forcing term is what it's usually called. Okay, so let's do an example right away. So an example that we can do, and where this kind of comes up, could be in physics. So say that you have a mass m on a spring, and let's say that this is my rest condition, so I'll call this x equals 0, and then my x is going to be changing with time. And then what I'm also going to be doing is pushing my mass back and forth, So think of it as you're just pushing the mass left and right over and over again. Okay. So how are we going to write down an equation of motion for this? Well, we're going to use Newton's law, so F equals ma, and then we're going to recall what a is. So what is the same thing as, so what is acceleration? Well, it's the derivative, should be m. So it's the derivative of velocity, so I can write velocity prime, right? But then what's velocity? So velocity is just the derivative of position, so I can actually write F equals ma as mx double prime. So then I can write mx double prime, which is equal to mass, or which is equal to F. So now I can try to find out what this F is going to be. Okay, so what is this F? So I'm going to have a force from the spring, right? So I'll call it force spring. And then I'll also have a force coming from drag, right? So there's going to be some friction on the surface, so let's call it force drag. And then I'm also going to have my forcing term right here. I'll say f of t, right? Some forcing term. Force is a function of time, so f of t. Okay, so then we can just easily plug in what f of spring is. Okay, so if my string is pulled this way, right, my string is going to be pulling me back to the left, so that's going to be minus kx. And then we have force drag. So if my velocity is going, again, this way, maybe I could do it in a different color. So if my velocity is going this way, that means that my force drag would be going this way, right? So it's going the opposite direction of force drag. So we can put minus some coefficient of friction, b, times x prime, because x prime is the same thing as velocity. And then we have some forcing term. So remember, we're saying that we're pushing it back and forth. So let's just call it cosine of omega t, right? So we're just oscillating it back and forth at a certain angular frequency omega. Okay, so this equation then goes to mx double prime equals minus kx minus bx prime plus cosine omega t. Okay? So after this, we want to get all the x's to this side and all the t terms to this side. So this is easy enough. We can just add the x terms to the other side. So we get mx double prime plus bx prime plus kx is equal to cos omega t. Okay? Just one more quick point on the getting all the x's to this side. Think of it just as your like 9th grade algebra course. Remember when you're doing like separation of like separating variables, like get all the y's to one side, get all the x's to the other side. It's the exact same thing here. Yeah, so we're back to this equation right here. So this is going to be an inhomogeneous equation. Okay, so how do we solve these inhomogeneous equations? Well, how I kind of remember it is that we can always write it with a plus 0 right here. So we can say that I can just solve this kind of independently. I'll have two kind of, I think of it as independent solutions that I can just add together at the end, and I'll get my same exact answer. So the first thing I do is solve the homogeneous equation. So the homogeneous equation goes to mx double prime plus bx prime plus kx is equal to 0. Okay? We went over how to solve this, remember? So we just do the characteristic equation is m lambda squared b lambda plus k is equal to 0. This is a quadratic equation, so we can solve for lambda. So lambda equals negative b plus or minus square root b squared minus 4 times a, which is m, times c, which is k, all over 2 times m. Okay, so I'm going to call this lambda plus and lambda minus. That's not a minus, that was a 2. But lambda plus is going to be the plus part, and lambda minus, which is going to be the minus part right here. So then we get the solution. X as a function of time, right? Because this is going to be oscillating in time. So I'll just use that as my variable for time. It's going to be equal to some constant c1 e to the lambda plus times time plus c2 e to the lambda minus times time. Okay? So now the second one is what we call the particular solution. So for the particular solution, it's going to be the kind of tricky part, because we actually have to solve this differential equation, which is kind of the big problem here. Like, this wasn't a problem, but this one will be a problem. Okay, so what is the solution to this? So basically you're going to get a few instances of like the f of t or f of whatever variable you're differentiating with respect to on this side. So this is a instance where we have a cosine of omega t. So when we have a cosine of omega t, we just kind of think logically and we say, okay, I guess, because I kind of know it's going to be a solution, that my solution is going to be in the form x with respect to time is going to equal some constant a times sine of omega t plus some constant b times cosine of omega t, right? So I don't know that it's going to be just a cosine oscillation or just a sine oscillation, but I am pretty sure that it can be some combination of both of these. Okay, so I guess that it's this. So now I can say my x prime of t is equal to a omega cosine of omega t plus negative b omega sine of omega t, and then I get x double prime with respect to time, so just differentiating x prime now again, we get negative a omega squared sine omega t minus b omega squared cosine of omega t, right? So now I can plug all three of these back into this equation over here, and I can get m, so this is going to be a lot to write, so I'm just going to kind of cheat a little bit and copy and paste it. If you guys are going along with the video, you can always pause it and write it out yourselves. But, you know, usually people just skip over the algebra parts that are pretty easy, just duplicating stuff like this, because they don't need to learn how to write. So anyway, that was a good kind of side note in order to not make this so boring, me putting all this stuff down here. Okay, so we have all this stuff, and I actually need to move this over a little bit. So yeah, these equations can actually get kind of big, as we see here. But they simplify out really nice. Okay, cool. So we finally have an equation, which is cosine omega t on this side, and some sines and cosines over on this side. Okay? So now we say, that doesn't look like an easy equation, Toby. What am I supposed to do here? But it actually is kind of an easy equation. So remember how we do partial fractions from calculus 2? It's the exact same thing here. So we note that this is a 1 here, and then we can also write 0 sine omega t, right? I can always add 0 times anything to any side, and it won't change the equation. So now we just have to match our coefficients 1 and 0. Okay, so let's match all of our cosines. So what am I going to have for cosine coefficients? So I'm going to have one from right here. So this is going to be negative mb omega squared. And then I'm going to have one right here, which is going to be plus ba omega. And then I'm also going to have a third one right here, which is going to be plus kb. So we know that this is going to have to equal 1. And then we also have my sine terms. So my sine term is going to be here. I'll do the sine term in a different color. So my sine term is going to be here. It's going to be minus m a omega squared right here minus b omega. And then right here is going to be plus ka. And that must equal 0. Okay? So now we note, or now we ask ourselves kind of what are the variables we're trying to solve for here. So the variables that we're trying to solve for is our a's and our b's, right? Because we're going to be given an omega from our problem, right? They're going to be telling us, okay, you're forcing it at this frequency, you know, like 1 hertz or something like that. So we're going to be given an omega. Our k is just going to be from my spring constant, right? They're going to tell us how strong our spring is, if it's really easy to pull apart, or really hard to pull apart. And we're also going to have our small b term, right? It's going to tell us how much the friction against the table is. And we're also going to know the mass of my object that's oscillating, right? The mass at the end of the spring. So the only things that we care about are our a's and our b's. Okay, so now how do I solve for my a's and my b's? So this is a pretty complex equation. If you're given actual values, I would highly recommend putting it in a matrix form. So this is going to be, I'll put a's here and b's in this row. So it's going to be b omega, and then it's going to be k minus m omega squared. And then looking in the bottom row, at my a terms is here and here. So that's k minus m omega squared. And this is b minus b omega for the b term. It's going to be a b. Just tells you that the a's are on the left side right here, and the b's are on the right side right here. And then we have that's equal to 1, 0. And then you can just plug this matrix into your, well, technically this and this matrix into your calculator, and then do row reduced echelon form, which we'll go over later in the linear algebra part of this course. But for now, it doesn't really matter. So we'll just go over how to solve this. So how do we solve this function, or this set of equations right here? So the first thing that I'm going to do is going to get the, why not, just do like a's by itself on the top. So we have, actually I'm going to get b by itself on the bottom because it's going to be easier with this 0, right? So we have ka minus m omega squared a all over b omega is equal to capital B. Okay, so I can plug this into my top equation. So I get minus m times omega squared times this whole thing right here. So that's my b plus b omega a plus k times this whole thing right here is equal to 1. So now that's one equation with one unknown, right? My only unknown are going to be my a's right here. So I could solve for this, and then I could plug that back in. So then I get a equals some solution. And then I can plug this solution back in to here to find out what b's are, right? So then I can get b equals b solution. Okay, so now finally what I can do is go all the way back up here and find out what my guess was. So my guess right here, so I'll copy it and paste it back down. So I finally got my a solution and I got my b solution. So I can finally plug this back in. So I have x of t is equal to a solution sine omega t plus b solution cosine omega t. And then remember, this is called the particular. So then again, we're almost done with the problem. So remember up here, where did we do it? Oh yeah, right here. So remember right here, we had a superposition. We basically added a 0, so we'd have a superposition. Just basically a superposition just means that you add another term. So we say that our x total solution with respect to time, right, because that's how we're defining how our object moves, is with respect to time, is going to be equal to x particular plus x homogeneous. Okay, so if we plug this in, we get my x particular is equal to this right here. Then we get my x homogeneous was what we solved up here, and that was kind of the easy one, remember? So my x particular, or homogeneous, is right here, where my a solution is right here. My b solution comes from right here. And then my lambda plus and lambda minus come from right here. Cool. So now we actually solved this equation, and all we're going to need to be given is 2 initial conditions in order to solve for C1 and C2, and then we're done. Cool. So this is already kind of a long video, so I'm going to stop here. Look out for the next video, and I'll be able to go over some more of the general, let's say y double prime plus y prime plus 10y is equal to some f of x, right? Where x is my differentiation variable, so y prime is defined by dy over dx. And I'll be going over what to do when we don't have a cosine here. And these are actually the easier ones. Cosine is definitely the hardest one. So I decided to do the hardest one first. Sorry about that. If you want to, just look at the future video. What would that be? Probably video 10 instead of video 9, and then come back to this video 9 if you want like a physical example of where these pop up and how kind of fun they can be for solving physical problems. All right. I hope you guys enjoyed this video, and I will see you next time.